Welcome to the deep dive. Let's start with something, well, incredibly familiar. You've probably checked a clock today, right? Glanced at your phone for the time, maybe even pulled up a map.
Sure, happens all the time.
We do these things constantly, often without really thinking. But stop for a second. How do we actually know how long something takes? Or, how far away it is? How do we measure this stuff?
That's a great question. It seems so basic, but it's actually quite profound. Humanity has been wrestling with this for ages.
Yeah.
We sort of take these measurements for granted, but figuring out how to define and quantify them, that's been a huge scientific journey.
Absolutely. So today, that's our deep dive. Time and distance, these fundamental concepts. Our mission really is to unpack the methods, the history, the breakthroughs.
And even some of the philosophical tangles that pop up when you try to nail down what is time or how do we measure space.
Exactly. Prepare for a trip that might make you look at your watch or maybe even just a ruler a little differently. We're going from the tiniest fractions of a second.
Like the lifespan of a subatomic particle.
All the way out to the edge of the observable universe. It's going to be quite the ride.
And guiding us through this, we're drawing heavily from a chapter in a classic, the Feynman lectures on physics.
Yeah.
It really pushes you to think about these basics in a, well, fresh way.
Okay, let's get into it. Time. It feels so intuitive, but defining it. Where do we even start?
Well, Feynman, he puts it in this almost Zen-like way. He says, time is what happens when nothing else happens.
Haha. Okay.
Yeah.
Which is helpful. It kind of highlights how slippery it is.
No, it really does. It's not something you can easily point to. So maybe the definition isn't the main thing.
Right. It's the measurement that matters. That's where the science actually happens.
Precisely. And this is where someone like Galileo comes in, over 350 years ago. He was a game changer.
How so?
He shifted things. Before him, it was a lot of philosophical debate, often going back to Aristotle. Galileo said, no, let's make quantitative observations. Let's measure how far and how long.
You can almost picture him, can't you? Rolling that ball down a slope, but not just watching, measuring, carefully noting how far it went in a certain amount of time.
Yeah, and the source points out something interesting. Measuring the distance wasn't the big hurdle. People were pretty good at that.
Oh, okay.
The real challenge was measuring short bits of time accurately.
So what did he do? What was his clock?
Believe it or not, his own pulse. He'd count his pulse beats to mark off equal time intervals as the ball rolled.
Wow. Okay, but hang on. Your pulse isn't perfectly regular, is it? How could that be properly quantitative?
That's a really sharp point, and it gets to why his work was so important. It wasn't about getting perfect precision right off the bat.
Okay.
The crucial thing was establishing a consistent unit for that experiment.
Yeah.
It let him see the pattern, the relationship.
The d proportional to t squared thing. Distance is proportional to the square of time.
Exactly. That relationship, that was the leap. Defining time, even imperfectly, by a repeating event he could observe.
Okay, that makes sense. It's about finding something that repeats. A periodic event, like the sun rising and setting, a day.
Precisely. The cycle of a day is a natural periodic event. But, as Galileo suspected, even days might not be perfectly identical. How do you check?
You'd need another clock to compare it to.
Right. The source suggests using something like an hourglass, a good, reliable one.
So you'd, count how many times you flip the hourglass from noon one day to noon the next?
Yeah, noon being when the sun's highest.
Yeah.
And if you consistently get the same number of hourglass turns per day,
then you can be pretty confident that both the day and the hourglass are reasonably periodic. You're kind of defining time by their agreement.
Exactly. It's a definition built on consistent observation.
Okay.
Okay, so we have the day, but we need smaller units, much smaller.
Enter Galileo again with the pendulum.
Yeah. He noticed, apparently, while watching a swinging lamp in a cathedral, that a pendulum swings back and forth in equal time intervals, as long as the swings are small.
That led to the pendulum clock. Right, a huge improvement over using your pulse.
A massive improvement. But science didn't stop there. We needed even shorter times.
So beyond mechanical things.
And we moved into electrical oscillators. These things can vibrate incredibly fast and consistently. We're talking periods down to like 10, 12 seconds. Picoseconds.
How do you even see something happening that fast?
Great question. You need special tools, like an electron beam oscilloscope. It basically acts like a microscope for time, letting us plot these super fast electrical signals.
Turning electricity into a clock. That's clever. But even that must have limits. What about times that are just unimaginably short?
Right. For those, direct counting is out. We have to get indirect, often using distance and speed. This is where it gets really wild.
Okay, hit me.
Consider the lifetime of a particle called the 10 Melisson, or pi 0 meson.
Okay. Subatomic particle.
Yep. It exists for only about 10/16 seconds. That's
Yeah.
10 millionths of a billionth of a second.
Right. You definitely can't time that with a stopwatch or an oscilloscope.
Not a chance. So how do we measure it? We usually see the tiny track it leaves in, say, a photographic emulsion, before it decays or disintegrates.
Ah, so you measure the distance it traveled.
Exactly. And if we know its speed, which we can figure out from its energy, then distance divided by speed gives us the time it existed. Simple division, but for an incredibly tiny time.
That's mind-bending. Using distance to measure time at that scale, 10/16 seconds.
And it gets even shorter. Physicists talk about things like nuclear vibrations happening on scales of 10^24 seconds.
Okay, that number barely registers. What does that even mean?
To give you a sense, that's roughly the time it takes light, the fastest thing there is, to cross the nucleus of a single hydrogen atom.
Whoa.
And it forces you to ask, does our normal idea of time as this smooth-flowing thing even make sense down there? What does it mean for something to happen in 10^24 seconds?
Yeah, that pushes the boundary of the concept itself. Okay, so that's the incredibly short scale. What about the other end? Measuring really long times? Ages, not seconds.
Well, we've always used natural recorders to some extent. Tree rings, layers of sediment in riverbeds. Those give us clues going back hundreds, maybe thousands of years.
But for like the age of the Earth or fossils?
For that, we needed something else, radioactive dating. This introduced a completely new kind of regularity, not just periodic repetition, but predictable decay.
The half-life idea.
Exactly. A radioactive element decays in such a way that half of its atoms transform in a specific constant time, its half-life. Then half of the remainder decays in the same amount of time, and so on. It's beautifully predictable.
So if you know the half-life and you measure how much of the original radioactive stuff is left compared to its decay product,
You can calculate how long it's been decaying, how old the sample is.
like carbon-14 dating.
That's a classic example for organic stuff.
Uh-huh.
Carbon-14 has a half-life around 5,000 years. By measuring the remaining C14 in wood, bones, whatever, we can date things back, up to maybe 100,000 years.
And for things like rocks. Really old stuff.
We use isotopes with much longer half-lives. Uranium, for instance, has isotopes with half-lives in the billions of years. By comparing the uranium to the lead, it decays into within a rock.
You can find the rocks age. And some are billions of years old.
Several billion, yes. And this method, applied to rocks and also meteorites, is how we've pinned down the age of the Earth itself.
Which is?
Around 4.5 billion years. It's remarkably consistent between Earth rocks and meteorites, suggesting they formed around the same time from the same primordial stuff.
And that fits into the bigger picture of the universe's age.
It does. Our best estimates put the beginning of the universe, the Big Bang, somewhere around 10 to 12 billion years ago.
Which brings up that philosophical point again. If time began with the universe, can you even ask what happened before the beginning? Does the question make sense?
It's a question that bumps right up against the limits of physics and philosophy, a real head-scratcher.
Okay, so we have these incredible methods, but the standard of time itself has also evolved, right? We didn't always have atomic clocks.
Absolutely not. The quest was always for a better, more universal clock. Galileo used his pulse, then pendulums. For a very long time, the Earth's rotation was the standard.
A second was defined as a fraction of a day.
Yep, 186,400th of the average solar day. That seemed pretty solid for a while.
But there's always a but in science, it seems.
There often is. We eventually discovered, with more precise measurements, that the Earth's rotation isn't perfectly steady. Days vary slightly in length, and the average is slowly changing over centuries.
So our fundamental clock, the Earth itself, was wobbling a bit.
In a manner of speaking, yes. So we needed something even more stable.
Enter the atom.
Exactly. Atomic clocks. These are based on the incredibly stable frequencies of vibrations within atoms. They are fantastically insensitive to external conditions like temperature or pressure.
Like the cesium clocks.
Cesium clocks are the workhorses. And the source mentions Professor Norman Ramsey's hydrogen atom clock, which he thought could be even more accurate. We're talking accuracies of 1 part in a billion, $199, much, much better now.
And it's not just abstract precision, is it? This accuracy underpins so much of modern life.
Oh, absolutely. Think about GPS. Your phone, figuring out where you are, relies on comparing signals from multiple satellites, and the timing has to be accurate to nanoseconds. Without atomic clocks, GPS just wouldn't work reliably.
Global communications, financial markets.
All depend on this incredibly precise, synchronized timekeeping based on atoms humming away consistently. It's a huge shift from watching the sun to counting atomic vibrations.
Okay, that's time. Mind-boggling scales, incredible precision. Let's switch gears to distance. How far? How big? Does it follow a similar path? Starts simple, gets complex.
Very similar arc, actually. It starts basic. You get a stick, maybe call it a meter stick. You count how many sticks long something is. You make smaller marks, millimeters, microns. Straightforward comparison.
But you can't use a meter stick to measure the height of a mountain or the distance to the moon?
Right. So just like with time-needing indirect methods, we need indirect methods for large distances. The classic one is triangulation.
Using angles, like surveyors do.
Exactly like surveyors do. If you have a baseline of known length and you measure the angles to a distant object from both ends of the baseline, you can calculate the distance to the object using trigonometry.
And this works for astronomical scale.
Oh, yes. The source mentions measuring the height of the first Sputnik satellite about 500 kilometers up using triangulation from 2 points on Earth. Even the moon's distance, nearly 400,000 kilometers, was measured this way early on.
So 2 telescopes on Earth become the ends of your baseline. Clever. What about planets?
For planets, we first mapped their relative distances using Kepler's laws and observation. Getting the absolute scale, the actual number of kilometers, was harder. One way was to triangulate on a nearby asteroid like Eros as it passed by.
Use a closer object to calibrate the whole system.
Kind of, yeah. But now we have even better methods, radar.
Like bouncing radio waves off things.
Exactly. We can send a powerful radar pulse to, say, Venus and time precisely how long it takes for the echo to return, since we know the speed of light very accurately.
Time plus speed gives you distance. A totally different definition of distance, almost, based on light travel time.
It is, and crucially, where they overlap, these different methods, meter sticks, triangulation, radar, give consistent results. That builds confidence.
Okay, planets are one thing, but stars, they're vastly farther away. Triangulation must get harder.
It does. You need a much bigger baseline than just 2 points on Earth.
What's bigger than the Earth?
Earth's orbit around the sun. We measure a nearby star's position against the background stars, then wait 6 months until Earth is on the opposite side of its orbit and measure again.
Whoa. Using the diameter of Earth's orbit about 300 million kilometers as your baseline.
Precisely. That works for nearby stars. But many stars are too far even for that. Their apparent shift, the parallax, is too small to measure accurately.
So another clever workaround needed.
Indeed. Astronomers figured out a relationship between a star's color and its intrinsic brightness, how bright it really is.
How do they know its real brightness?
By studying those nearby stars whose distances were known from triangulation. They saw a pattern. Stars of a certain color generally have a certain absolute brightness.
Okay, so measure a distant star's color?
Infer its true brightness based on the pattern.
And then compare that to how dim it appears to us. The dimmer it looks, the farther away it must be, like judging the distance of a headlight at night.
That's the perfect analogy. And the fact that this method gives consistent distances for whole clusters of stars, like the globular clusters mentioned in the source, gives us confidence it works.
That's really ingenious, and that helped us map our own galaxy.
It did. By mapping the distribution of those globular clusters, astronomers realized they weren't centered on us, but on a point much farther away. That helped pinpoint the center of the Milky Way, about 10-20 meters from here.
10 followed by 20 meters.
Okay. And knowing roughly the size and type of our own galaxy helps us estimate distances to other galaxies.
How? Assuming they're similar.
Basically, yes. If you see a distant spiral galaxy that looks like ours, but much smaller in the sky, you can estimate its distance based on its apparent angular size. Like maybe $3, 10, 20 meters away.
And we can see galaxies even farther than that.
Oh, yeah. The giant telescopes, like the Palomar telescope mentioned, have photographed galaxies so far away their light has been traveling for billions of years. We think some are maybe halfway to the edge of the observable universe.
Which is roughly?
About 10 meters, an almost literally astronomical number.
Makes you feel rather small, doesn't it?
Puts things in perspective, for sure. Okay, so that's the vastness. Let's flip it. Let's go small, really small.
Down past millimeters and microns.
Right. Microscopes let us see down to microns, 10⁶ meters. But visible light itself has a wavelength, around half a micron, 5 times 10⁷. That sets a limit on the detail you can see with light.
The wavelength barrier. So it needs something with a shorter wavelength.
Like electrons. Electron microscopes use beams of electrons, which have much shorter effective wavelengths, letting us push down to maybe 10 dimeters. Small enough to see individual large molecules like viruses.
Okay, getting closer to atoms. How do we measure them?
We can't see atoms with electron microscopes in the traditional sense of forming a clear image of their boundaries, but we can use techniques like X-ray diffraction. Shine X-rays through a crystal.
And the way they scatter reveals the regular spacing of the atoms.
Exactly. That tells us atoms are about 10 meters across. Angstroms.
But then there's the nucleus inside the atom, which is way smaller, right?
Way, way smaller. There's this huge jump in scale. Atoms are 10 meters, but the nucleus inside is only about 10-15 meters. That's 100,000 times smaller.
Whoa. Okay, so definitely can't see a nucleus. How on earth do you measure that?
Back to indirect methods. We use particle scattering. It's like trying to figure out the size of invisible boulders in a field by randomly throwing pebbles and seeing how often you hit one. We fire high-energy particles, like protons or electrons, through a thin sheet of material. Most particles zip right through the empty space in the atoms. But occasionally, one hits a nucleus dead on and gets deflected or stopped.
So you count the hits.
Essentially, yes. The fraction of particles that get scattered tells you the total target area presented by all the nuclei. From that area, you can calculate the radius of a single nucleus.
And that radius is about 10, 15 meters.
That's the scale, yes. We call that unit of Fermi.
Another incredible inference from indirect evidence. But does it go smaller? Can we measure distances inside a nucleus or even smaller still?
That's where current physics is pushing. Theories about the fundamental forces, like the strong nuclear force or even string theory, suggest that our basic notion of smooth, continuous space might break down at incredibly small scales, maybe even smaller than a nucleus.
So space itself might get weird,
Yeah.
grainy, different.
It's a possibility. Our concept of distance might need revision at those scales, which, again, echoes how our standards have evolved.
Right. The meter stick itself hasn't always been the same definition.
No. It started as a fraction of the Earth's circumference. Then it was the distance between two scratches on a platinum iridium bar kept near Paris.
The famous bar in France.
That's the one. But even that isn't perfect. Now, the meter is defined based on the wavelength of a specific frequency of light emitted by a particular atom, or related to the speed of light, much more fundamental and universally reproducible.
So looking back at all this, it's clear our definitions of both time and distance aren't fixed truths. They're tools, operational definitions that evolve as our science gets better.
Precisely. And each new definition, each new method, is tested for consistency against the old ones in the regimes where they both apply. That's crucial for building a coherent picture.
But then comes the real kicker, relativity, which tells us these measurements aren't even absolute.
Right. This is where it gets truly fundamental and a bit strange for our everyday intuition. Einstein's theories of relativity reveal that measurements of space and time are not the same for all observers.
So, if you and I are moving relative to each other, and we both measure the time between two events or the length of an object,
we won't necessarily get the same answer. Your now might not be my now, and your meter might not be my meter.
That's so counterintuitive. It means space and time aren't just a fixed background stage for events to happen on. They're part of the play itself, affected by motion and gravity.
Exactly. They're interwoven into what we call space-time, and its geometry is dynamic. It shows how deeply connected distance, time, and the observer really are.
And then there's another layer of limits coming from quantum mechanics.
It gets even more fascinating. The laws of quantum physics themselves seem to impose fundamental limits on how precisely we can measure certain pairs of quantities simultaneously.
The Heisenberg uncertainty principle.
That's the one. There's a fundamental fuzziness. You can't know both the exact position and the exact momentum of a particle at the same time. The more precisely you know one, the less precisely you know the other.
And there's a similar relationship for time and energy.
Yes. There's a limit to how precisely you can determine the energy involved in an event if it happens over a very short time interval, and vice versa. It's tied to the wave nature of matter itself.
So perfect precision is impossible, not just practically, but fundamentally.
According to our current understanding, yes. The universe has a built-in level of uncertainty, of indeterminacy at its core.
Which makes you wonder, if reality itself is fundamentally fuzzy at that level, what does that imply about the nature of existence? It's not just about measurement limits, it's about what reality is.
That's a deep question. And it shows how measurements aren't just about finding numbers. They're about probing the very nature of reality and discovering its perhaps unexpected rules.
Wow. What an incredible span we've covered. From trying to time a rolling ball with a pulse
To using atomic vibrations accurate to parts per billion or better.
and measuring distances from the width of a nucleus 10, 15 meters.
All the way out to galaxies 10 meters away, near the edge of what we can even see.
So as you've been listening, what stands out to you? Has this changed how you think about just glancing at your watch or figuring out how far away something is?
Because it seems clear that our quest to measure, to quantify time and distance, isn't just a scientific exercise. It's deeply tied to how we understand and define reality itself.
And maybe the most profound takeaway is about those limits we bumped into: relativity, quantum uncertainty. They hint that the universe, at its deepest levels, might be interconnected and, frankly, stranger than we currently imagine. Perhaps those unanswered questions about the tiniest times and distances hold the key to the next big revolution in understanding what it means to be.
A fascinating thought to end on. It really makes you reconsider the foundations.
It certainly does. Until next time, keep exploring.